All right, we're at chapter 18, Thermodynamics. Dismiss my image and get started. This lecture will help you understand thermodynamics, absolute zero, the lowest possible temperature that any substance can reach, internal energy, the first law of thermodynamics, adiabatic processes, meteorology, and the first law. The second law of thermodynamics, order tends to disorder, which is another way of saying entropy. Entropy always increases. Things move from an ordered state to a disordered state. We'll get into that. Okay, the science of thermodynamics was developed in the early 19th century. Atomic and molecular theory of matter was not well understood. So early thermodynamics invoked macroscopic ideas such as mechanical work, pressure, and temperature. The two foundation stones of thermodynamics are number one, the conservation of energy, and two, the fact that heat flows spontaneously from hot to cold and not the other way around. Okay, as the temperature of a gas changes, its volume also changes. At 0 degrees C, with pressure held constant, volume changes by 1/273rd for each degree Celsius. Um, so you can see at 100 degrees, it's 1 plus 100 over 273. At zero, um, it's 1 volume, it's 1 minus 100 over 273. And at minus 273 or 0 Kelvin, the volume is zero. Now, that's theoretical. Um, the You don't ever really get to zero volume of uh, any gas. There's always going to be some molecules there, but that's the, the lower limit. So absolute zero, this is the lowest limit of temperature possible. They've never reached it. They've gone to a few microkelvin, but nobody's ever reached absolute zero. Minus 273.15 Celsius. Um, at this point, molecules have lost all available kinetic energy. There's very little motion. Um, okay. Internal energy. Internal energy refers to energy at the molecular and particle level within a substance. The internal energy of a substance is quite complicated. Its simplest forms are the kinetic and potential energies of its molecules. Our study focuses not on the internal energy per se, but rather on changes in the internal energy of a substance. If you recall, in the last chapter, we talked about a gram of water going from ice at minus 50 to zero, then melting, then the water warming up. From the minus 50 to zero of the ice, we were increasing its internal energy. We weren't increasing its temperature. We were increasing its, we were increasing its internal energy. We weren't changing its phase. It was still ice, but we were changing its internal energy. Um, our study uh, focuses not on the internal energy per se, but rather on changes in the internal energy of a substance. Okay, here's some common points. I kind of did something similar with that line graph. Maybe this is a little more easier to see. We know that, let's go from top to bottom. 212 degrees Fahrenheit is 100 degrees Celsius, and that's 373 Kelvin. That's uh, that's the boiling point of water. And the normal body temperature, 98.6 Fahrenheit, 37 Celsius, and 310 Kelvin. Notice I don't say 310 degrees Kelvin. That's a misnomer. It's just 310 Kelvin. On a warm day, 77 degrees. Obviously, whoever wrote this didn't live in South Texas. Uh, 25, 25 degrees Celsius and 298 Kelvin. Room temperature, 68 degrees, 20 degrees C, and 293 Kelvin. And then the freezing point of water is 32 degrees Fahrenheit, 0 degrees Celsius, and 273 Kelvin. Okay, and these are just some absolute temperatures. We go 0 Kelvin here, helium boils, oxygen boils, dry ice vaporizes, dry ice doesn't melt, it just vaporizes. Um, uh, ammonia boils, ice melts at 273 K, water boils at 100, 400 Kelvin, at it looks like a 200 degrees C, like 475, 10 melt, and then 1800 Kelvin. Notice they've stopped the Celsius on the left-hand side. Iron melt. Um, you have a carbon arc lamp, uh, 4,000 Kelvin. I actually worked I was actually a sound man for a ballet company, and I worked at the one of the places we went was at the Paramount Theater in Austin, and they had a carbon arc lamp, and boy, that thing was bright. You didn't dare look at it. Um, I'm talking about the internal burning of the carbon rod. That thing was bright. It was hot. Okay, at 4,300 Kelvin, all molecules are broken up. No solids or liquids. At 20,000 Kelvin, you get plasma. That's ionized gases. The um, 50,000 Kelvin surface of a hot star. The center of our own sun is 20 million Kelvin, and then a fusion reactor is 100,000 Kelvin. I'm sorry, 100 million Kelvin. Let's see. Okay, the first law of thermodynamics. The law can be stated that the heat added to a system transforms to an equal amount of some other form of energy. Heat added to the system equals increase in internal energy and the work done by the system. So increase in internal energy plus work done by a system. We'll see that this is the basis for a heat engine. The first law of thermodynamics is the restatement of the law of conservation energy. Energy can neither be created nor destroyed. Okay, here we have a small experiment. Instead of adding heat, if we do mechanical work on a system, we can expect an increase in internal energy. That is the temperature rise. We'll see the temperature rise. So it says rubbing your hands makes them warmer. That's one example. You're applying the friction that you get between your hands. It warms your hands up. And then Joule's apparatus. As the weights fall, they lose potential energy. That's mechanical energy. And that is converted to heat that warms the water. So as these things drop, these weights drop, that spins the little paddles, which adds energy to the water and heats it up. Okay, when work is done on a system, for example, compressing air in the tire pump, the temperature of the system increases, decreases, remains unchanged, or is no longer available. Well, it increases. If you've ever pumped a tire with a hand pump, like a bicycle tire, you feel the cylinder getting warm. In accord with the first law of thermodynamics, work input increases the energy of the system. And that's the end of this first part. I think we actually covered two sections from chapter 18.